Okay, here's a review problem for the final exam. This is a heat transfer problem. It involves a tumbler, to keep your iced tea cold in the summer. And the thing to think about here is that there's a plastic layer, and we're given the thickness of that is 0.1 centimeters. And then there's an air gap, and then another plastic layer. Okay, so when you read through this, the question is going to be, how large should the air gap be to meet this specification for the heat transfer rate per unit area? Okay, so the problem statement actually has the formula that we're looking at. It's the change in temperature divided by the sum of thermal resistances is equal to the heat flow per unit area. All right, so what we know here is that Q over A is 200 watts per square meter. All right, and then we also know some constants. We know the thermal conductivity coefficient for air and for plastic. For plastic, it's 0.5 watts per meter per degree Kelvin. And remember, Kelvin and Celsius have the same degree size, so that's equivalent to 0.5 watts per meter per degree C. Okay? All right, so the reason that's significant is we need to pay attention to the units. All right, so we're looking at this. This is a metric system. The thicknesses and the areas should be in meters or square meters. The temperature should be in degrees Celsius or degree Kelvin. In this case, we have it in degrees Celsius. And the measure of energy flow is watts, okay, energy per unit time. All right, so with that being said, what we're looking at here is that the Q over A, which we know that number, is going to be the delta T over our plastic plus our air plus another our plastic. Now the thicknesses of the plastic are the same, so this becomes delta T. If you look at the problem statement, the delta T is 38 minus 10, so that's 28 degrees. All right, then we have 2 RP plus RA. Okay. All right, so next we need to solve, if we solve for RA, we can get the thickness, right? Because in the problem statement, the resistances are delta X over K. We know what K is for air, and so if we found RA, we can find the thickness. All right, so hopefully that's obvious to you. If not, think about it until it becomes obvious. All right. Okay, so next we need to eliminate this RP variable, and we can because we know the thickness of the plastic. Okay, so again, paying attention to the units, we were given that the thickness of the plastic is 0.1 centimeters. Okay, so what we have to do is convert centimeters to meters because we need this to be in a dimensionally consistent set of units, and the values for the conductivity have meters. Okay, so we convert that to meters. All right, and so we get 0.001. All right, and then that's RP. That's delta X, and we divide by K. The K is 0.5, and so we get 0.002 for RP. All right, so then that lets us solve for RA. So doing a little algebra here, we know that Q over A is 200. This would be 28 over 2 RP plus RA. All right, solve for RA. Okay, so that looks like that would be 28 over 200 minus 2 times RP. Okay, so when I do that calculation, I get that RA is 0.136. And you can keep track of the units here. But for the purposes of this solution, I'm just going to not put that in. All right, then delta X over K, all right, for air, the K value is 0.03 is equal to 0.136. This is the thermal resistance of air, the air gap. Okay, that lets me solve for delta X. When I solve for delta X, I get 0.0041, and delta X would be in meters. All right, and so often we would convert something like that to a more easily visualized measurement. So